Welcome back, guys. So we have this new force, this centripetal force. Let's try to set up some problems and solve some problems with it. So our new F net is going to be mv squared over r. The first thing we're going to have to do, just like we did with F net equals 0, F net equals ma, is to draw a free body diagram. Then the thing that's going to change is that instead of taking ups minus downs or rights minus lefts or counterclockwise minus clockwise, we're going to take forces towards the middle minus forces away. So there has to be something towards the center. Something has to be turning it. You don't have to have one away. So that's why we do towards minus away, because this one is necessary. Once we have that, we will set that equal to mv squared over r. All right, so going over a hill. What is my free body diagram? And we're going to say that just on the guy sitting in his chair. So for that one, I'm going to say that mg is going down and n is going to go up. Mg is necessary, n isn't. So roller coaster people realize this in circular motion, that you can get it going over a hump just fast enough where the normal force will disappear. It's going to be a specific speed. You've probably felt this if you've ever been on a roller coaster or been driving in Amish country, you go over a hill, you feel like you're lifting out of your seat. That's your normal disappearing. All right, so for that one, I'm going to say F net equals mv squared over r. I'm going to take my forces towards the center minus away. The center of my circle would be here. And so it's going to be mg minus n equals mv squared over r. The normal isn't necessary. So the normal could be 0. If n is equal to 0, then our mg is equal to mv squared over r. The m's cancel. And our speed equals radical gr. So if you're an engineer, you can easily plug in your acceleration due to gravity, the radius of your circle, and you could find out exactly how fast you need that roller coaster to go over that thing so everybody lifts out of their seat. And the interesting part is, doesn't matter how much they weigh because the mass cancels out. All right, on to case 2. Now I'm upside down. mg is still going towards the center, and it is possible that n is going towards the center as well. And so I'm going to say that F net equals mv squared over r. I'm going to take my forces towards the center, minus away, and this is going to be mg plus n equals mv squared over r. And again, we can't get rid of gravity, but normal could be 0 in this case as well. On to case number 3. Now I'm at the bottom of the hill where I feel like I'm being pushed down. mg is now still going down, but my n has to be longer because the n has to balance the mg and turn it. And so when I do my F net equals mv squared over r, I'm going to go towards the center, minus away, and now I have n minus mg equals mv squared over r. So those are our 3 situations. We have mg minus n, mg plus n, and n minus mg for the same roller coaster. It just depends on what part of it we are. All right, a man spins a tennis ball around in a vertical circle with a radius of 0.5 meters at 6 meters per second. What is the force required to maintain the circular motion? So this centripetal force is equal to mv squared over r. So this is going to be equal to 0.3 kilograms times 6 meters per second squared divided by 0.5 meters. So the force required to maintain the circular motion is going to be 21.6. So when I add those forces together, that's what they're going to end up being. Now I'm going to look at the highest and the lowest points. So I have the highest and the lowest points. I'm going to center this thing because somehow it's quite off. I'm not sure why it's off, but it is off. So when I'm at the top, I have tension going down and I have weight going down. When I'm at the bottom, I have tension going up and I have weight going down. This one needs to be longer than that one. So when I'm at the top, F net equals mv squared over r. I'm taking forces towards the center minus away. So I have T plus mg equals mv squared over r. And again, you don't have to have away. Circular motion requires something towards. So my tension is mv squared over r minus mg. So my mv squared over r I know is 21.6. And in this case, the tennis ball is helping us turn because it's also pointing towards the center. So this is going to be 0.3 kilograms. I forgot the mass of my 18.6. All right, when I'm at the bottom, F net is also equal to mv squared over r. But now when I take my towards minus away, I have T minus mg equals mv squared over r. So now my tension is going to be equal to the centripetal force plus the weight. So now this is going to be 21.6 plus 3 newtons, or 24.6. So my tension has to do two things when it's at the bottom. It needs to turn the ball, to accelerate the ball by turning it, and it also needs to lift it. All right, a 1,200 kilogram car is traveling at 25 meters per second around a turn of radius 150 meters. What is the centripetal acceleration of the car? The force of friction, the minimum coefficient of friction to keep the car from slipping. All right, so we need a car. Here's the car. It's coming straight at you, and it's going to come out of the smart board, turn around, go into Dr. Turner's room, and come back out. So the center of the circle is somewhere there. What is the free body diagram on this? It would have mg going down, normal going up, and then lowercase f that represents friction going to the right. All right, so I want the centripetal acceleration. This is going to be v squared over r. So this is going to be 25 meters per second squared over 150. And so I got 5 meters per second squared. What is the force of friction? The force of friction, I need to look at my F net in that direction. So I have two problems. Up and down, I have F net equals 0. The normal and the weight are going to balance out. In the X direction, I have a circular motion problem. So I'm going to take the force towards the center, minus away, and towards the center is friction, and nothing is away. So friction is going to be equal to mv squared over r. So this is going to be 1,200 kilograms. Our velocity is 25 meters per second. Our radius is 150 meters. I have a force of friction of 5,000 newtons. What is the minimum coefficient of friction? Well, I need N for that, right? So we're saying that friction is less than or equal to mu N. If it's the minimum, it's equal to. I'm saying that's what it has to be at least. So what is it when it's equal to mu N? So that's like in the lab where I had you guys pull a block and it was right as it let go. We were concerned with that. So I need N. Well, in the Y direction, it's essentially at rest. It's not moving. So F net equals 0. I'm going to take up minus down. So this is going to be N minus mg is 0. So N is going to be equal to mg. So N is going to be equal to 1,200 times 10, which is 12,000. And then I can manipulate this equation by dividing both sides by N, and I get that my mu is equal to my force of friction over N. Mu is a ratio, like pi, so it's unitless, but it's 5 over 12, or 5,000 over 12. Which is about 4.2. Remember I said tires are around 1, so this car should easily make this turn. As long as something is not affecting the coefficient of friction, like ice, snow, that would definitely make a difference.